So in this video we will work again with R factor, but this time we will create R factor by our own using Google Earth Engine script. Before starting, I want you to point attention to this article which I will attach. So systematic review of the incorrect use of an empirical equation for the estimation of the rainfall erosivity around the globe. So it was published in recently, I think 2023, yes. 2023. So it made the review of all the possible mistakes which were done by the different researchers when it comes to estimation of the rainfall erosivity factor. Initial rainfall erosivity was derived from the Zweisheimer publication, but according to the authors, the researchers incorrectly converted the unit from one to another. That's why this led to different kinds of mistakes. So you can read the research's article. So the most frequent incorrect formula was this one. This formula which was commonly used. Further investigation indicates that there are even more papers published with incorrect versions of the original equation for P. Arnold was 1997. So the correct formula is this. After correcting the unit and conversion errors is as follows. So this is the correct formula. So we will use the correct formula. Here I recommend you to read this article. It's very interesting. Before also we will use this image collection, CRISP Daily, Climate Hazard Center Infrared Precipitation with Station Data. So 5,566 meters pixel resolution. It contains only precipitation. So it starts from 1989 till now. So the pixels resolution is approximately 30 square kilometers, which is not very accurate, but it's very sufficient for the precipitation and in general climate data. Let's start. So I uploaded this file global database. So the beginning is the same. I upload, I filter my study area, and I convert it to geometry. Also, I uploaded this image collection for precipitation. The next, aggregate daily crisp rainfall into monthly precipitation sums in millimeters. So I will use this. This is a daily estimates precipitation. So I will aggregate dailies to monthly. Using this function, I will create monthly rainfall, image collection, sequence from the first to the last month, map function. So for the year 2024 data set, and I will filter based on the calendar range for each month, select days in the month, and sum and set the attribute value. And I can test here this January image. So let's so far close this one. This is a January image. See, so let's test. So this is my study area, and this is January rainfall. So see, it works for a global January rainfall aggregated. Let's stretch and see. This is from 0 to 302. It's in millimeters. It's in millimeters. Yes, it works. Again, my bad liar. Now I will create mean precipitation. Again, I will use this dictionary from lists, list sequence, return string, format months as for 01, 02, list sequence, monthly data, filter. So it's calendar. So calendar range, I will use the scale 5000, maximum pixels, geometry, reducer mean. So it will get mean precipitation values. So far it's for globally, but it doesn't matter. We will clip it afterwards into for our study area. So compute p square for each mass and total. P square, it's in the formula. Where is yeah, this one. It's monthly precipitation, average monthly precipitation square. So p square monthly rainfall. I will map again function return image multiply image, so it's a square, rename p2, which is p square, reduce so sum p square over all months. Yes, after I will compute all the months square, I need to sum it. So see, it's a sum. I need to sum all the square of the monthly precipitation. Then I need to compute this one. It's a total annual rainfall. Total rainfall, monthly rainfall, reducer sum, rename total rainfall. I can yeah, let's debug it. Let's see what we have so far. So mean precipitation, yes, it's for January, etc. And a layer total rainfall, we can see here. So yeah, it's total rainfall. We can stretch it. Yeah, it's annual rainfall, so it's relatively high precipitation area. So especially these areas have approximately 1000 even in some areas. So I will again check. Then we need to divide p squared, divide to total rainfall. So we're doing this one. So dividing sum of the square of the monthly precipitation into the annual rainfall, and this is called term. I will use the function term. So again, let's see what we have. We can see the term. I think it will be the global term. Yeah, I didn't clip so far, so we can clip it anyway, but let's see what we have for the globe. It's a global area, so it's divided one. We can see stretched. It's yeah, it ranges for different areas. Term. Yes, term. My area somewhere here. Where is it? Yeah. Anyway, so the next step is to compute R factor using logarithm. So we will compute different types of logarithms. Bear in mind, because this is not, this equation is not universal, it's more empirical equation. So for some areas this equation might work well, for others you need to adjust it. So first, a logarithm, I will multiply term, this one, to 1.5, subtract 0. This value, multiply 17, and yes, rename R factor exponent, rename R factor logarithm. The next, I will try to compute R factor using logarithm 10, base 10 logarithm. The same, but this function differs. And let's see what we have. And the last is my adjusted logarithm. Again, logarithm 10 here. But here see that I changed it. So if it's written here 1.5, I change it to 2. So we see what the results we have. Let's run. So it's not a very complicated code, as you can see, and it's faster. So this is general totally term. Let's see R factor logarithm. You used the conventional formula, natural logarithm. So see that it is too high. See, for my study, from 2400 to 12,000, it is very high. I think it's unreliable. And now this is a more this is natural logarithm, this is actual logarithm. So this kind of logarithm in Google Earth Engine, name it as logarithm 10. R factor logarithm 10, I stretch and see that it looks suspiciously small. If you remember, for my for the rainfall Gloreda map, for my study area, according to Gloreda, of course we cannot trust Gloreda as well, especially for the Central Asia, because they didn't share the weather station parameters. Anyway, they used interpolation. So, but anyway, it looks suspiciously small. Especially this is a more or less rainfall area, from 92 to 100. Let's check. So even despite that I used completely correct formula, it looked suspiciously small. So now I used, instead of 1.5, I used 2. See, now it looks like more reliable. So at least minimum values are completely the same. Minimum values are the same. Maximum value is twice smaller comparing to the Gloreda. This one. Yeah, its minimum value is the same, see? But the maximum value this here is well, it's very looks big. I should use the stretched. Well, it's too many classes. Let's use single color. Apply. See, some places, well, it depends on the interpolation as well. So let's go to the Gloreda original, and I want to see where is my study area. So it's here. Let's use identificator. Yeah, it might reach 1000 sometimes, certain areas, but the interpolation also played its role in well, it's played its role in increasing the maximum value. Its maximum values are smaller, minimum values are the same. So what we can do again, we can adjust one more time. Let's put it here 2.2, and I also changed the subtract value. Probably I need to change subtracts even. Let's write it 1.5. Again, see what we have. So you have to adjust it to your study. Yeah, it's decrease. So minimum value also increased, but the maximum value also increased. It's close to 1000. I can continue adjusting, but the minimum value is satisfactory, and if it will continue to grow, I think it won't be very reliable. Therefore I will stop here. So again, you need to adjust to your study area. First do research, and also compare with Gloreda. Probably you will do you have this study area information. So yeah, it's here. In rare areas it reaches 1000. I think this one is the last one, is the most reliable. So I will finally upload this R factor adjusted. So I will upload R factor adjusted, and I will use it for my RUSLE analysis. If your values, like final values, looks unrealistic as it looked for my previous R factor, which was computed exactly based on the equation, see, it's too small. It's twice smaller, even less than twice smaller. comparing to the minimum value, and oh my god, it's like 6 times smaller than the maximum value. But of course, I'm comparing with Gloredo, it might be also incorrect, but I think this is the more realistic values. Gloredo, of course, probably maximum value is overestimating, even so it's mountainous areas. See, these are the mountain areas. Usually for this kind of areas, maximum value of R factor reaches 800, 900. Also, we should take into account, yeah, probably this year was for 2024, it was very high precipitation. R factor changed year by year, so R factor can change year by year and month by month. Of course, you can work with monthly as well. You can download monthly. So there is January. I took a image, monthly rainfall to list, get 1, get 2, get 3. You can check monthly R factor as well. Well, it's a precipitation, but you can change took the R factor as well. So our R factor for Gloredo and computed by our own based on the equation is ready. If you liked the video, you can consider purchasing the whole course, developing a high-resolution RUSLE model in QGIS, where I show how to develop a 10-meter water erosion model in QGIS with the help of Google Earth Engine in Saga. The link to the course in Udemy you can find below.